All right, everybody, welcome back. So, in our last section, we were talking specifically about what characteristics we look for in order to distinguish living things from non living things. So, in this lecture, we're going to really be breaking that down into a smaller unit and really looking at the chemistry and molecules that really characterize and classify life. So, again, this is probably going to be a lot of review for some of you, but this is really just to be able to contextualize the important reactions that we're going to be talking about and understanding the chemistry that sort of exists at the base of all of these different syntheses that we're going to be discussing. So, when we're talking about this in a scientific context, we're talking about matter. So matter is anything that takes up space and critically has mass. And all matter is made of elements. And these are substances that cannot be chemically broken down. So it's the sort of the base unit of matter. So the smallest unit of an element that you can possibly have is an atom. And atoms have distinct chemical properties. And again, this isn't a chemistry course, so we're not going to be going in depth into any of these next few slides. But what I'd like you to be able to recognize is that when we're talking biologically about these different syntheses and different molecules, that you know that's the chemistry at the base of these is really what is driving these processes forward, and we have to have a base understanding of these properties in order to appreciate the overall synthesis and processes that are happening in biology. So atoms are determined by the number of subatomic particles. So the nucleus is this dense core of an atom, and that is made up of both protons and neutrons. Protons are the positively charged particles, and neutrons are uncharged particles. And then lastly are electrons. And again, I'm sure you've already had all of this in previous science courses, but this is just to give you a quick refresher so that it's not confusing when we start talking about the chemical reactions in life, in biology. And lastly, so the electrons are these negatively charged subatomic particles, and they orbit the nucleus. So the best way to describe these elements is the periodic table. And it's a way of reporting at its base the atomic number and the atomic mass of all the different elements. However, what's the structure of the periodic table of elements actually provides us with a lot of different information. It helps us to identify the size, the neutrality, and the similarity between different elements. So this is just a summary looking at a couple different ways that the periodic table is organized. So for example, in the center here, oops, sorry, I was trying to get my cursor, but apparently that's lost. So when we're looking at across the table, we're seeing increasing of ionization, magnitude of electron affinity, and electronegativity. So you can describe the different elements based on where they are in the table and understand not only its similarity to other elements, but how it's going to be reacting with different molecules. And as we go across, we get decreasing atomic radius. As we go up, we get decreasing atomic radius. So again, this structure of the periodic table really has enabled us to understand the similarities and differences of each of these elements, and also it's enabled us to discover new elements because we're able to ascribe differences and similarities between elements that are near one another. And I have a great video that sort of talks about the history and organization of the periodic table. So when we're talking about biology, the element that is by far the most important is carbon. So it's the fourth most common element in the universe, and it's the second most common element in the body. And really, again, when biologists are thinking about life on other planets, we're thinking about specifically the different elements that make up that are the most important here on Earth. So oxygen, carbon, hydrogen, nitrogen, phosphorus, and sulfur. And if you recall, in our sustainability lectures, we talked specifically about how these different elements cycle throughout the Earth. So again, these are the most important elements. So understanding not only that they are the most common, but how they circulate through the environment is ultimately what's really important about our ecosystems and driving biology sort of forward. So again, carbon is that key component of molecules of living organisms. And the reason why it's so important is it can form these covalent bonds where it's able to share a pair of electrons between two other atoms. And because of this, molecules can be linked by these covalent bonds, and you can add up these atoms into four different structures. And so you can see here we have a common structure of carbon bonding with four other hydrogen atoms. And because carbon can form multiple covalent bonds, it becomes sort of the key component to the structures that we're going to be talking about in living organisms. And when we're talking about organic molecules, again, we're going to be talking specifically about carbon, and specifically carbon molecules that have these carbon backbones. So you can see here structurally we have this hexagonal structure, which would be called a hexane in biology. Oh, actually, no, this is not a hexane. Sorry, there's only five. But if you take any sort of organic chemistry, you'll come across the hexane quite intimately. But what we're critically trying to understand here is that organic molecules have what's called these carbon backbones. So you have this structure of interlocking carbon, and then you have at least one carbon-hydrogen bond. So anything that has this structure is going to, in this case, this is glucose, we have both this carbon backbone and we have at least one of these carbon-hydrogen bonds, and that's what makes up an organic molecule. Inorganic molecules, however, lack that carbon-based backbone and those carbon-hydrogen bonds. So here we just have carbon dioxide, which is carbon bonded to only oxygen atoms in this case. So again, difference between inorganic and organic molecules is really that structural backbone and that carbon-hydrogen bond. Okay, and we're going to pick up next time where we're really going to start to explore organic structures and understand the chemistry behind those structures. So I'll see you soon. Okay.